So for section 7.3, we're going to be doing population means instead of proportions. But the process is still the same. I want you to make sure that you're checking P, R, T, C. So first, state the row. Specifically, this time it won't be P equals because we're already dealing with the population mean. So we'll start by saying mu is equal to the true population mean of whatever it is. Okay? R, we will check the requirements. There are really two that we worry about. First, we need a SRS. Same as before, either data must be collected randomly. If they don't state it, sometimes they'll say it was collected randomly, they'll just put SRS. So if it's there, you just say stated. If they don't state it, then we're going to put assumed. I still want you to run it. What you do, though, is if I give you a question, let's say that describes the sampling and it was done completely biased, then you would say, no, this doesn't work. It was not randomly selected. This test won't work unless we have randomly selected data. And then second, we have to have normality. How do I get normality? Either I know the population is normal, or the central limit theorem, basically. If the sample size is greater than 30, then the central limit theorem checks out, and we will get normality. That's why that central limit theorem is such a big deal when we're talking about means. Or we can check it. We can check normality. So if we don't have a sample of 30, if we have like 28 or 27, doesn't mean we throw it out. We could check it visually. We could check a histogram. And we could check the shape for normality. I could check a box and whisker plot. And I would want there to be no outliers. And last, I could do a normal probability plot. And I would want that to be linear. If that follows along an approximate line, then those would be things that we could sketch out and then show, it looks pretty normal, we can probably run this test. So that's the P, the R, the T. We're going to state the test. Our test is going to be either a T or a Z interval. Okay? They'll say T. T interval is if sigma is unknown. Now keep in mind, we very rarely know the population standard deviation, so more often than not, we're going to use the T interval. But you know me, there's going to be a question where we're going to be estimating, and I will give you a sigma. There are times in real life where we would know sigma. So we would say, or, if sigma is known, then instead of a T interval, we can use a Z interval. And the Z interval, once again, is just because sigma is known, we could actually use the Z-score for that. We'll talk about what a T is as we keep going. Okay? And then we'll state our conclusion, and the good news is the conclusion is literally word for word how we had our last one. So before we go on, I want to make sure I recap kind of a big idea that we started with here. Kind of had this conversation before where if I'm doing a confidence interval, okay, I'm dealing with the sampling distribution. If I take all the different means, all of them, and I plug them into a distribution, we get this sampling distribution, right? Where the mean of the means equals the true mean, standard deviation is sigma over square root of n. All of this we know by the central limit theorem. Okay? Well, in chapter 6, we said we expect 95% of all the means to be within 2 standard deviations. So if I go there and I go 2 standard deviations to the right and 2 to the left, most of these means should fall within there. So mean 1, 2, 3 didn't, 4 didn't, 5 did, 6 did, 7 did. This is an 8 apparently, so 8 did. So a lot of them fall in 2 standard deviations. About 95% of them would fall within 2 standard deviations from the truth, right? That's chapter 6. Chapter 7 says, I don't know the truth. So what do? Well, we take each of those means and I do a confidence interval off of the mean. I go right and left 2 standard deviations from the mean. And what we say is if I go 2 standard deviations from the sample statistic, we believe it will contain the truth, not all the time, about 95% of the time. If I do an interval, why does it need to be right or left? Because I don't know where the truth is. Here the truth was to the right, here the truth was to the left. But basically any of these numbers that had fallen within 2 standard deviations, the truth would fall within 2 standard deviations of it. Okay? So that's the idea between Chapter 6 and Chapter 7. Chapter 6, we expect 95% of means to be within 2 standard deviations. Okay. Chapter 7 says, well, then if I take that mean and I go 2 standard deviations on either side, I expect it to contain the truth. About 95% of the time. Right? And then how do we phrase that? Well, we use this statement like we did before. We are, or I am, blank % confident that the true mu, true p, whatever it is, will be between a min and a max. Okay? I like to take a little bit of time here because we have a formula for this confidence interval. It's basically that it's going to be, I'm going to make sure the statistic plus or minus the z-score times sigma over square root of n. Now there's also statistic plus or minus, this is called the margin of error. And remember this smaller piece, we call that the standard error. But rather than just give you this formula, we could actually take a formula that we had before for z. And what if I took that formula and I just solved it for mu? What if I wanted to get that mu by itself? Well, I could multiply that scary denominator out. Goodbye, goodbye. I'm left with x bar minus mu is equal to z times sigma over square root of n. I want to solve for mu, so I would subtract the mean away. What I end up with is the negative mean plus z times sigma over square root of n is equal to negative mu. Solving for mu, divide by the negative. I get mu is equal to x bar minus z times sigma over square root of n. Well, that's very similar to the formula that we have over there, isn't it? Well, sort of. Keep in mind, we don't know where the error is going to be. It could be on the right or the left, which is why we make this a plus or minus, because the error could go on either way. Oh, this didn't line up, did it? Okay, so we don't know where the actual truth is. We know that it could be, let's do this. We know that the x bar falls in the middle, and if I go plus or minus the margin of error, that it should give me the truth. And the other thing we do is we put a little star on the z. Why do we put a star on the z? We get that z from the confidence level. So the confidence level, to get z, we do inverse norm, confidence level plus 1 over 2. And that will give us that z-score, just like it did before. The only other thing I want to talk about, because I said we're not just going to be doing z distributions, we're also going to do t. What a t distribution is instead of z, we use t. They're like, well, why? Because we don't know sigma. If I don't know sigma, I can't use this formula, right? So if I don't know sigma, what we do is we use s over the square root of n. This up here was for a z interval. This down here is for a t interval. These are the ones we're going to be using the most. Keep in mind the calculator will do a lot of heavy lifting. But how do I get that t-score? Well, t is equal to inverse t. Confidence level plus 1 over 2. There's one other thing you have to include here. It's called the degrees of freedom. Why the degrees of freedom? Well, because the t-distribution basically says if I don't know sigma, I cannot use a z, I cannot use a normal distribution. But I already know the data falls pretty normally. So what the t-distribution does is it opens up wider, it allows for more error depending on your sample size. So the degrees of freedom is basically the sample size minus 1. We've seen this before. We did the formula for standard deviation. We divided it by minus 1, and I called it degrees of freedom then. Okay? So basically, the t-distribution changes depending on the sample size. So I'm going to look at the calculator and see how that works. On graph, you don't have to do this. I just want you to kind of see this. I can graph a normal distribution by doing norm, NORM. PDF, I think, is what I have to do for the picture, though. And then it is an X, mean, and standard deviation, I think. Let's see if that does it. Ta-da! There's a normal distribution. Doesn't look very normal. We'll keep in mind that normally our distributions don't go from -10 to 10. So what I can do is I can zoom this in. So let's zoom it, not from -10 to 10, let's go ahead and go -4 to 4. And I also don't need the y values to go from -6 to 6. So how about 0 to, I don't know, 0.6 maybe, should be plenty of space. That looks a lot more like our normal distribution, right? So here's our normal distribution. The question is, how does the t-distribution differ? Well, let's see. Instead of norm PDF, what if I did t PDF? And so I can graph it with different x's. But I also have to include, let's see, degrees of freedom. So I need 0, 1, degrees of freedom. So let's say we sample 10 people. And 10 people would have degrees of freedom of 10 minus 1, 9. I think that'll work. Let me see. Too many arguments. I don't think I need the mean. I think I just need the 9. So just put that. Okay? So the x with degrees of freedom of 9. Okay? There we go. Gosh, that looks a lot like the normal distribution, doesn't it? But they're not exactly the same. Notice that the red, the t-distribution, is a little wider. It allows for more error. Why does it allow for more error? Because we don't know sigma. And so just because I don't know sigma doesn't mean I can't estimate the truth. We just have to allow for a little more error so that we will contain the truth. Okay? Notice if I change that from 9 to 5, that would be a lot more error. It gets wider. Okay? What happens to the t-distribution as the sample size increases? Well, what if instead of sampling 10 people, I sampled 100 people? And now degrees of freedom would be 99. Right? Are these now identical? Well, if I zoomed in, I'd probably get closer and closer and closer. But the idea is, what if I sampled like 1,000 people? Right? 1,000 minus 1. Basically, these start matching up almost perfectly, right? And so the t-distribution just basically says, I don't know sigma, so I'm going to allow for a little more error. That's what the degrees of freedom does. So what are we going to do in the homework? It's really, I'm making this a lot more complicated. I just want to make sure we understand kind of what we're doing. PRTC, P, state the parameter, R, check the requirements, T, we said run the test. You're going to be doing a T for the homework, okay? There are a couple examples on the quiz where I will give you sigma, then run a Z. It's not a big deal. And then C, how do you state the conclusion? And I wrote that down earlier, but I'm going to put it here. I am blank % confident that this time don't put P, because we're not dealing with P, we're dealing with mu, the true mean, is between, and we'll put a min and a max. Okay? So let's go through one example and see how to do that. National Student Loan Survey collects data to examine questions related to the amount of money borrowers owe. They selected 1,280 borrowers, the mean of the debt of the sample, and the standard deviation. Keep in mind, this mean is not the truth. This is the mean from the sample. This is an X bar. This standard deviation is not the standard deviation of the population. This is S. Okay? So what I'm doing with this is doing a 95% confidence interval, and I'm going to use a T distribution or Z. Well, if sigma is unknown, we will use a T distribution. Okay? What's PRTC? P. What is our parameter? The mean debt for the student loan borrowers. And I need units, so I'm going to put in dollars. What are the requirements? Really two that I need to worry about. You could argue independence still, but we don't emphasize that as much, so I'm not going to make a big deal. What do we need to do? Collect at random. But this time, I don't need to write assumed, because they said the survey was done randomly, so it was stated. Now, if I found out later on, I did some research and found out that they did bias in their sampling, then we throw it out. Okay? What else? I need normality. Do not say, oh, I need at least 5 successes. There's no success in this. We're doing an average debt. It's not like debt is success, right? What we do here is we say, I either need to know it's normal. Did it say that? Didn't say anywhere that it's normal, right? Or I need a central limit theorem. Well, what's our sample size? It needs to be bigger than 30. Well, we have 1,280 borrowers. 1,280 is way more than 30. So the central limit theorem kicks in. We've got normality. T, what test are we going to run? It's called a one sample T interval. You could also do this with the formula. Oh, not Z, sorry about that. T times S over square root of N. Or I can do this in my calculator. I'm going to let the calculator do the heavy lifting at this point. So let's go back to a calculator page. Menu, statistics. We're doing a interval. Which one? A T interval. Data or statistics. We have two choices. Data means I'm inputting just some, I have an actual list of data. So I have the actual list of data and I can run it. We don't have that, we have the statistics. What was the X bar? 18,900. Standard deviation was 49, really sad, was it 1,000 or 100? 49,000, that's really depressing. And our sample size, 1,280 borrowers. And our confidence level, they said, was 95%. So I can leave that. Okay. We have a lower and an upper, 16 to 13.1. And the maximum, wrong one, of 21586.9. This is not done. You must state the conclusion. I am 95% confident that what? I don't have to restate it. We did it up here. That mu the mean debt for all these students is between $16,213.10 and $21,586.90. Okay, and that's it. Like I said, it really isn't that hard. The more we practice it, the easier it's going to be. And the calculator will do a lot of this heavy lifting for us. So let's go ahead and keep going on these. See, make sure that, like I discussed, that we discuss the units of measure somewhere, and that it'll be the same as the original data, but that needs to be stated. And the round off rule, just make sure that I actually encourage you, if you're doing the formula by hand, just keep as many decimals as you can until the very end. They recommend at least one more. Using the summary statistics, use the same number of decimal places as they use in the sample means. That gives you kind of a broad way of handling that with the homework. So at this point, what we're going to do is we need to type these numbers into a list, and we're going to go ahead and run a t interval on that. So go ahead and make sure you have these typed into one list. So I'm going to put this in my list A. And what we can do is we can actually run one of our stats. We could run one of our stats and get the mean and the standard deviation and run the test manually. But you actually can run the test in the list. So if you need to, go ahead and pause this for a second while you input the list. But I'm going to go ahead and start on the PRTC, so our P parameter that we're dealing with. Everything in this section is going to be means, but you need to make sure you differentiate, because on the test you're going to have means and proportions, and you need to know, what am I starting with? Well, they said the population mean weight of discarded paper. So this would be the true average of discarded paper garbage. Paper garbage. Okay, our requirements. Well, did it say that this data was collected randomly? It doesn't. So when I'm doing this, I'm going to go ahead and assume it to run the test. That wasn't helpful. And I'm not going to write stated this time because it wasn't stated, so I'm going to write assumed. If I find out later on that this doesn't represent a random sampling of discarded trash for the day, then this would not be something to generalize with. Okay. Second, how am I going to get morality? Well, did they state that it's normal anywhere? Does it say that this is a normal population? They didn't, did they? You're like, that's okay, because essential limit theorem. Okay. Well, essential limit theorem, we need at least 30, right? Do we have at least 30? Now, if you're done typing this in, you'll see that this is 20 numbers. N equals 20, N equals 20, so that's not large enough. Okay? So what do we do? Well, we're going to have to graph this, and we're going to have to look at it. Okay? So go ahead and wait now, but hopefully you have the data typed in. Like I said, there should be 20 numbers. Because we're going to do some graphs, we're going to check normality. We need to make sure we name this. I'm just going to name it, how about trash? Okay? Because I need to get a couple sketches to see what this looks like. So I'm going to go to my graphs, fifth one over. We're going to choose the trash. Right off the bat, not the best way to tell. You can use a histogram, but with a small set of data, this isn't terribly helpful. So if you sketch this and tell me it's not normal, I'm going to say, yeah, you're really not the best thing you should be looking at. You should be looking at other things besides a histogram here. Okay? What I would prefer would be a box plot. Right? Are there any outliers? See, that looks roughly symmetric. There's a line around the center. These tails are about the same length. So I would sketch that. So I would go and the line was a little bit to the left. That's roughly normal. This is just a sketch, right? I don't need an exact, this is just, and I'll be able to tell if you're just sketching these and if you're just making these up. Make sure that it actually looks like the graph from the computer, because I'll have people that'll just like sketch a box plot and go, it's normal. No, you need to check it. I'll be looking for that, okay? And then last, go to plot type and choose a probability plot. And I want to see that these dots are following mostly along this line, okay? And we're going to sketch it again. And so when I say a sketch here, I'm going to start with 2 dots. And then kind of a curve up, down, and back up. Curve kind of upward, downward, and back up. But overall, this basically looks roughly normal. This would be good evidence for normality. Most of the points are falling along that straight line, and there was no outliers. Okay, which means let's run the test. What test are we running? Well, sigma, we do not know sigma. So if sigma is unknown, we will run a t interval. Menu. Alright, go back to the data. Sorry about that. Go back to the data. Menu. Statistics. They have intervals and tests here as well. So I go to the interval. We're doing a t. Notice if I do z, even if I have the actual data, it's asking me for sigma. That should stop you. You're like, well, it didn't give me a sigma. Then don't run that. Run the t interval. Just a little more error. This time I have the actual data, so I can run it on the data itself. Our list is in A. Our confidence level, I think they said 90%, so we need to change that to 0.9. And put the results somewhere away from our original data. If I scroll up, it's the same little output they gave me before, but what's nice is they put it in the table for me. So 7.649, I'll round that to 7.65. And 10.6. So what is our conclusion? I am 90% confident that what? Well, what did we just estimate? The true mean of the weight of the discarded paper, right? So that mu is between 7.65 and 10.6. What though? See, that's kind of irritating. So I'm dealing with the business, and I don't know if these are pounds, if these are tons. So really, this is kind of a poorly weighted. I should have units here. Some unit of weight. They didn't give it to me, so I wouldn't penalize you for that. But the idea is that you should put those units. The maximum breadths of samples of metal Egyptian skulls from 4000 BC and 150 AD. So do we think that head changes size over time? Or heads get bigger, they get smaller, right? Well, changes in head size over time suggest interbreeding with people from other regions. Okay. Use a confidence interval to determine whether the head sizes appear to have changed from 4000 BC to 150 AD. So was there a change? What they did is they have a bunch of skulls from back then. They measured the breadth, so how wide the skull was. Here they measure the breadth of people from 150 AD. Was there a significant change between these? Okay. So the key here when I'm doing PRTC, oh, by the way, if you're working on this right now, make sure that you type these in. This would be my list A. And this will be our list B. And we're going to do something with those in a little bit. So if you want to make sure you type those in. So we are going to be dealing with the average head, but we want to know whether there was a change. So it's still going to be a mean, a mu, but it's going to be the mean difference or change in head size from 4000 BC to 150 AD, specifically for Egyptian skulls. Okay, well, what are our requirements? Anything in here? We do not know that this was collected randomly, so I'm going to assume that this represents a simple random sample. If I can find out later on that we pulled skulls from a region in Egypt that don't actually have Egyptians that live there, that maybe that would change things, right? So I'm going to assume it at this point. Here's our issue with normality again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is not greater than 30. We do not have normality yet. We need to know how to check it. Okay? So what we're going to do here, this is called a paired t-test. Basically what I'm going to do is I'm going to find the difference between these skulls, and then I'm going to find whether the average change was positive or negative. So going to my list again, we have, I think I have it right here. There you go. So the first skull's in A, second skull's in B. What I want to do is I want to do a test on the difference. This is actually not going to be my favorite way of running a test on this. We're going to learn in later chapters how to do a better test that will give us more accurate results. But for now, we're trying to just say, well, I could find the difference between these. 131 minus 136 is negative 5. 119 minus 130 is negative 11. And then I can see if there was an actual difference. I'm going to go ahead and do a quick command on here and say do A minus B. And just let the calculator do some of that quick calculating for me. Okay? And this, I'm going to name it, again, because we have to check the normality. I'm going to name it diff. I'm going to try to name it. There we go. D-I-F-F. Okay? So this is really the data that I'm going to be running the test on, is not the original data, but on the differences of the data. Okay? So if you go back, basically it's the negative 5, negative 11, 12, negative 1, negative 10, negative 15, negative 6, negative 6, negative 7, negative 3, negative 3, negative 1. We're running a test on the differences. Okay? Let's check normality. If I go to a graph, this time I'm going to choose diff. This doesn't really tell me much. I can look at a histogram, but with a small set, it's kind of hard to tell normality. It does look like it goes to a peak and then back down. So what would be a better option here? Well, I'm going to sketch this, but this tells me we have a problem. I need normality, and there should not be an outlier, right? So I have this number kind of stopping here at negative 1, and then this 12 is a definite outlier. So, and then the line was out in the middle. And then out here is a outlier. That argues that it is not normal. What we would want to do is if we have that, then we basically need to just sample more points, sample more data until we have the central limit theorem. We don't have enough points. Find more skulls, basically, right? I will check the normal probability plot as well. And most of those points are following along, except we got this one loner kind of off of the pattern. This one's also a little bit off, but that one's kind of the one that's furthest off. So we'll sketch that. One, two, three. And then we have kind of these four. And then this guy's out here, all of them. That right there is off the pattern. So, not normal. So technically, I could just stop at this point and say the test is not valid, don't run it. I would warn you to do that on a quiz or a test. Like, that will happen sometimes. But if you write not normal and you maybe mistyped a number, you basically have thrown away half of the points for this question. Okay, so what I would recommend is I would recommend running the test, running the interval, so t interval, and then at the end, when we get to our conclusion, just add a little caveat and go, but results are not valid because requirements were not met. Okay, so I would add that. I'd still run the test, and then I would just put that at the end. How do we run the test? Well, I'm running it on C, on the difference. Statistics, interval, T interval. We have data this time. Stats, again, is if they said here's the mean, here's the standard deviation, I actually have a list of data that's in C. Did they specify a confidence level? They did not, right? So when you look at this and we say, okay, what is the confidence level if they don't specify it? We said 95%. If they state it, use what they state. If they don't, use 95%. Okay? So we're going to leave that alone, putting the results in D. I need the lower, I need the upper, negative 8.93. And the upper, negative 0.41. So you say, I am 95% confident that the difference, well, the mean difference in head size from 4,000, see, I saved myself a lot of effort by filling that in up here. So if you fill it in up here, first of all, you know what test you're going to run, so you know what requirements to check. It all helps, but then you don't have to state it again here. That the mu is between negative 8.93 and negative 0.41, and I think we were dealing with centimeters probably, or millimeters. Okay? But the results are not valid because the requirements were not met. I want to add one other little caveat because this is something we're going to do a lot more with later on. Whenever I do mean difference, was there a difference? Well, obviously the results were not met, because of the requirements. But if the requirements had met, would you say there's a difference here? Well, when I subtracted them, the average, the interval we got is negative. So if the interval is negative and negative, this implies there is a difference. Why? Because we got this by doing the first mean minus the second one. So if I do the first mean minus the second one, and it's both negative, it's less than 0, that implies that the first group was smaller than the second group. Okay? So I really, in this, am saying, I think the heads back in 4000 BC were smaller. At 150 AD, they got bigger. So either they just naturally get bigger, which I believe that is something that occurs, or there was an influx of another group that changed the population size. Okay. If the interval is negative, or if it's positive and positive, this also implies there is a difference. Well, why? Because that's the first mean minus the second being both positive greater than 0. That implies that the first group is greater than the second group. That's not what happened this time, right? But either way, if the interval is completely positive or completely negative, there is a potential difference. Our data suggests there's a difference. When is there no difference? What would no difference be, right? Not when the interval equals 0, but basically if the interval has 0 as a possibility. So if the interval goes from negative to positive, then what this means is there is potentially no difference. 0 is in the interval. There is potentially 0 difference. Okay? Doesn't mean it may lean more to the other side than the other. That's fine, but that means 0 is in there. It means there's potentially no difference. We would not have significant results there. Okay? And last but not least, we've done this before. Keep this in mind. I'll do this again real quick. This is taking our formula. This is taking the section that is called the margin of error. And we want a margin of error to be less than whatever we get. Okay? So the question is, again, what do I do here when I'm solving for n? Well, I multiply that up. Right? I divide over the margin of error. And last I square it. So that n, and I think I might have messed up with my interval in there, but n is going to be greater than z times sigma over margin of error, all squared. It's just that formula solved and set, basically set up and then solved for n. So this will give me an estimate for the sample size. Set this n is greater than or equal to, though. These are the same z-scores we had before. We're going to go ahead and use the z's. Technically, I could do it with t and say, well, depending on the sample size, and use a different t. And that gets really complicated. There are formulas for that, but we're not going to mess with it. We're just going to use these z-scores to get our approximate sample size that we want. Okay? So suppose you're interested in determining the mean number of hours spent studying each week. You want 95% confidence. That tells me z is 1.96. Maximum error of 0.5. That's our error. And the standard deviation of the population. I keep this in mind because if I do look at that formula, it did use sigma, right? We need the actual standard deviation of the population for this. So they're going to give me that. That 2.5 is sigma. So I say, well, n needs to be greater than the z-score times, I don't know, off the top of my head, times sigma over the error and all squared. So I'm looking at 1.96 times 2.5 divided by 0.5, and then the whole thing is going to be squared. So 96.04. What does this mean? 96 people won't do, right? I need more than that. We will always round this up. Always round this up because we're saying n needs to be greater than this. Okay? What if we wanted to decrease the margin of error to 0.25? Z-score would stay the same. Standard deviation would stay the same. Error would be now 25. So I go up here, and snake that, and change that 0.5 to a 0.25. 384.16. So that means how many? 385. So those shouldn't be too tough. We'll do one more just to kind of look at this. In order to estimate mean ACT score, okay, I do this a little differently. This is not tested. There might be a couple of these in the homework. But basically they say if I take the range and I divide it by 4, I get an approximate about what the standard deviation is. Because this doesn't have a sigma. Right? So they say, well, there's generally about 4 standard deviations. So if it ranges from 35 to 1, that means there's a range of 34. And there's approximately 4 standard deviations. That gives me about 7.5 as my sigma. Okay? This is an approximation. So now I can take this and go, and it's greater than the z-score, 1.96, times our approximate sigma over our samples, over our error, and they want within 2 points. So 1.96 times 7.5 divided by 2. Take that whole thing and square it, and we're looking at about 54 people, 54.02. So that means how many people? Hopefully by now we got it. Round that sucker up. You cannot have 0.02 people. I need at least 54.02 people, which means I need 55 people. So that's it. So that's everything that's going to be on this section. If this is a little difficult or a little overwhelming, the good news is the next chapter builds on this. Okay, so it's going to basically take this and we're going to apply it to testing. If you are having a really easy time, you're like, wow, this isn't as bad as I thought it was going to be, then the next chapter is going to be just as easy, if not a little easier. Okay, so get these sections done and keep it up.